Okay, 7:30. Let's get started. We have like 71, 75 students. That's good. So where are we? So we started on the sequential circuits, and I think we were planning to continue on to the flip-flop today, that discussion. And then we'll move to the next lecture, lecture 8, which is like sequential circuit design, and we'll continue there. Okay, so any questions so far? I have some on the discussion section, I think. Let's see. Okay, so let me share that part. Let me share this one. Okay, so I see from Yavav, there are question, negative positive edge trigger D flip-flop. Yeah, we'll continue with that flip-flop understanding and discussion today. So just hold on to that thought. Asynchronous preset reset, yeah, we can also go over that part. Next one is from Christina, is from the flip-flop timing constraint. Let's see. When the clock becomes logic 1 for the second time, that means at this point, right? Then has not been stable for the minimum setup time. Oh yeah, that's not drawn to the scale actually. That's not drawn to the scale. Let's say it is on the setup time. It was stable for that, and then it is following that D logic onto the positive edge of the clock, but it will come little later, like clock to Q delay, clock to Q delay. Q is reflected a little bit later. It does not spontaneously go from one logic to another. As the clock edge arrives, it needs some time. That's the clock to Q delay, and that's why Q is going up a little bit after the positive edge of the clock. But yes, this diagram is not drawn to the scale.
Hey, Professor?
Yes.
I just added another question if you want to refresh, like whatever order you want to do them in, but.
Okay, sure. Okay, this one. Okay. Okay, let's come back to this one. Okay, it is the next topic after the D flip-flop we explain on that. Okay.
Got it. Thank you.
Okay. So about this D flip-flop, let's first look at the timing diagram in the slide that has been given and try to see what does it mean. What does it mean? So it will be like this. Share. Okay. So you see, like a flip-flop itself is composed of two latch. Like in the master side, we are using a D latch, and in the slave side, we are using an SL latch. So in a compact sense, this is like one D latch and one SL latch, and they are connected to the D latch, and output of the D latch is connected to the S of the SL latch, and that goes the Y bar where it's connected to the R of the SL latch. and clock is fed inverted. Like this that means D latch is basically will store the data, incoming data as in D uh, on when the clock is at logic high, right? So that's what you can see here. If you follow the pattern, the logic pattern incoming on the D, this is an independent pattern, right? It doesn't depend on anything. And then try to correlate the pattern of the Y, that is the output of the this D latch. You'll see that during the positive logic of the clock, Y is following D, right? So during the negative edge, D was 1 and 0 and 1. It doesn't matter. Y did not follow. Y was kept at 0. And then at the beginning of this high logic of the clock, it is basically going uh, following the D logic itself. See that during this time D was high, then went to low, and then it went to high again during the low clock logic, but Y did not follow. So Y is in turn following only the logic part in the window when the clock is high logic. So you can observe it in this timing diagram as a behavior. It's true always, right? Any questions so far? All right. Now we move on to the next one. See the Y, this logic is feeding the SR latch with the inverted control. Like clock is inverted, that means this SR latch will register or will store incoming value, which is from Y, onto it during the negative logic of the clock. So you see in this, if you follow the Q logic is following Y exactly during the low logic of the clock. So in this low logic, Y was 0, so Q followed that. In this low logic, Y was 0, Q followed that. It really is not following Y during the high logic because it's an inverted clock is connected to it. So that's the observation. So Y is following D during the high logic of the clock and then hold on to the last logic value during the low time. But Q is following the Y logic value during the low logic period of the clock and holding on to the latest logic value during the high part of the clock. So if you follow this observation further, you see that during this low logic, Q followed the high, right? Because Y was high, it becomes high, and then it stayed high till the next following logic when Y become low. So far with this observation, now forget this Y. Okay, now let's look at the observation D and the Q, how they relate with respect to the clock. You see, as if Q is registering the value of D which is at the falling edge of the clock, right? So here at this point, after this point, Q is 0, D is 0 at this falling edge. Okay, after that, D changes his value no matter what. The next falling edge, D was 0, Q is 0. Next falling edge, D was 0, Q is 0. Next falling edge, D was logic 1, so Q jumped to logic 1. Next falling edge, D is 0, so Q falling to logic 0. Next falling edge, D was 0, so Q stayed at 0. Next falling edge, D is at 1, Q jumped to 1. So as if at the falling edge, it is registering the incoming value, whatever the value on the D, in the overall flip-flop circuit. And that is we mean by negative edge triggered. Yeah, is that clear? Or you have more doubt?
Yeah, that's good. Now I get it.
Okay, so it's the same thing you do for the positive. Here, if you follow the diagram, and it's basically nothing but inversion of the clocks anyway, with the other way, that your D your D latch is storing the incoming value on the negative logic of the clock, and SR latch is registering or storing the incoming value from the Y at the higher logic or logic 1 of the clock signal. So, and that gives the phenomena that at the positive edge of the clock, that means when clock is transitioning from 0 to 1, at that point, whatever the D value is being stored inside this flip-flop as a whole device, and Q is jumping to that logic. It's following exactly that path on the positive edge of the clock. So that's the positive edge triggered flip-flop. Now back to the preset reset. Now these flip-flops, see, like I started with some like at the 0 time, I started Y as 1 and Q as 0, right? So how do we make sure it is actually that known state it has? Like here we started with Q as 0 and Y as 0. So how we can do that? We cannot guarantee it simply by having like a feedback circuit like this. Like we don't know exactly when we power up this circuit, we don't know what is the initial Q value is at this point, what is the initial Y value at this point. So we need to have a mechanism to set this output value to a known logic. And that's where the preset reset comes in. So what this preset and reset, at least in this circuit diagram, it shows that this logic is fed directly into the output part of this each logic, output NAND logic of this each of these latches. And then if we fed in a 0 on the P, and let's say R stays at 1 at that point, then we can actually force the Y to become 1, right? And which in turn, not in turn, which also force this NAND, the output from which, for which the output is Q, connected to the Q, that also logic becomes, we can force it to the 1. And with this feedback mechanism, the other terminal, Q bar and Y bar, will become 0 respectively. So that is the preset. And we can do the similar thing as if we are resetting these values, where we are placing R2 logic 1 and P2 logic 0. And in that case, it will set the Y bar terminal to 1, because 0 is the controlling logic of the NAND gate anyway. So if you send a 0 signal to one of the NAND gate, it doesn't matter what are the other input values are. It will make the output of the NAND to 1, which is a known logic, which will in turn make the Y output as 0. And similar logic applies here on the slave side. It will forcefully turn the output of Q bar, this thing as 1, and which will make in turn the Q output as 0. So this is all about setting up this sequential circuit in a known value. We start as a known value. Make sense, Yava?
Yeah.
Okay. So at this point, let's continue with these experiment that models we started. The flip-flop, right? So we started with this one, right? We made a D flip-flop somewhere. Oh, here is a D flip-flop TB, or there's a test batch file. Okay, we have a D flip-flop here. Okay, D flip-flop here, which use the D latch as a master and SL latch as a slave, and this is a negative edge triggered, and we had a test bench for that. And let's see how, let's try to simulate this D flip-flop and look at the wave pattern for this. So we will do TFFTB, load that, and then we will, maybe we can just, yeah, just for fun, we are making it on the data flow. It doesn't really matter. What is more interesting is to look at CD, okay, CD preset, EQ bar. What is NQ? NQ. Ah, no. Okay, let's load them on the web. Let's try to simulate it. Oops. Okay. Apparently it crashed. Sorry for that. Let me open up the models once more. Okay. Okay, all right. Library, work, test bench. Okay, and then all right. Anyway, hey, I will go there. And we want to look at the data flow. Okay, so we can run all. And what I want to show you as a folded view of this. How can we do that? Fold. Fold. Okay, getting somewhere. Fold. Okay, this is your top level D flip-flop schematic. Unfold.
Hey, Professor?
Yeah.
Is there anywhere for us to get the source code for this? And if you used a different one last lecture, I forget.
It's the same source code. At this
Is there a place, is there somewhere for us to get the source code for that? Or do you just want us to re-implement it ourselves?
So you watch the video, write yourself.
Okay, cool.
By the way, these codes will be useful for you on the project 3, just as tips I'm telling you.
Cool.
Okay, anyway, I was just trying to show you a master slave. Let's forget about that one. I need to click through the sum sequence. Anyway, let's look at the waveform here. The logic part you can actually look at and observe yourself by if you create this kind of test bench and circuit. But let's see. We are interested in clock and reset and preset, and then we'll see the D and Q in relation to the C. Okay, so look at these preset. I kept it as logic 1. So more interesting is a N reset. So N reset usually, like, we give that name such a way it kind of implies that its operation is on the negative logic, which is 0 logic. So reset is really happening when N reset goes to 0. So before that happens, see, the output of this QQ bar is really unknown. It is not known. It is not in a known state. So as soon as we basically make the reset to 0, you see the Q becomes 0 and Q bar become 1. Q becomes 0, Q become 1. That is meant by your like asynchronous reset or asynchronous preset. Means it really doesn't matter with respect to clock where it is coming. As soon as it comes, it just reset that whole thing. There can be another set of reset preset, which is a synchronous reset preset, which means like resetting and presetting action only happens after the active edge of the clock for that flop. Means if it is a positive edge triggered flip-flop, reset and preset either operation will happen only after that edge is done, after the clock reaches that edge of the positive edge. But we'll be dealing mostly with the asynchronous reset preset, where we can reset or preset flip-flops at any point of time, irrespective of the clock state. All right. So now let's follow the clock. Clock is this guy, right? So it is being toggling at maybe 5 nanosecond, going down at the 10 nanosecond, 15 nanosecond goes up, 20 nanosecond goes down, etc. And D is kind of randomly changing its value. Now let's follow the Q. So during the positive edge, it is, oh, actually negative edge trigger. This is the negative edge trigger flip-flop, right? So even on the positive edge, this guy Q did not follow D at all. Like D was fluctuating, but it's still stable at 0. Only at the point when it is going, clock signal is going down from 1 to 0, at that point, your D is at logic 1, and that's what your Q followed immediately after that point, right? Immediately after that point, Q become 1. And then it hold on to that till the next negative edge, where the D is 0. So after that point, Q become 0. So it is following the D at the negative edge of the control signal or clock signal in this case for this component. Make sense? Any question, anybody? Okay, now we can move on to the next one, which is from the sequential design circuit, which I think Friend has a question, which is this one, right? If reset affected the state not always the same way, we need to have a column for it. Yes, we need it. But like reset, I just placed it as a condition there, reset equal to 0, because reset equal to 1 is presumably will put everything to the state A. So in this case, in this specific circuit, probably we didn't need that. But for other circuit, yes, it may. It depends on the what type of circuit and what is the problem statement you are trying to solve.
Got it. Thank you.
Okay, but that problem actually is an interesting problem, and where is that? So we basically try to make this state diagram for that given sequence recognizer 1101, and we implemented that after the series of K-map transformation and optimization. What I did, I basically had a sample implementation of that in the Verilog. That is something interesting to see. Let me quit. It is not very stable, the Windows environment. So let me quit, restart my models once more. Okay, close the project. Can I close project? Yes, I can close it. Open, okay, recent projects. All right. So I have this one. This is a simple, not this circuit. This one. Let's compare it side by side. So I have two flip-flops here, right? And that's what we are given at DFF A and B. And what we define here is an where which is like AT plus 1, that is as A underscore TP1, and AT, that where is marked as A underscore T, and the other part is AT bar, which is coming out of the Q bar from the D flip-flop A. Similarly, we have BT and BT bar that is coming out of the flip-flop B. And then we have BT. Do we need BT plus 1? Yeah, we need a BT plus. No, we don't need BT plus 1 because X is directly connected to the D. So we can skip the BT plus 1 where as a definition. So what we did, we defined this AND to AND, okay, which is AT and BT. So I think this AND, this is coming from AT and BT is coming there. Yeah, it is right there. Output is W. And then we have other AND, which is ANDing between X and BT. So X and BT, X being the primary input to this one. And we are ORing between this AND output. So ORing between one and W1, W2, which sends to connect to the AT plus 1, AT plus 1. So we are connecting to that where. And then output, as output logic, it is AT BT bar X, which is like X BT bar, which is coming out, will be coming out from the flip-flop B, and AT. Okay, so I ended that become output. And state machine, simply I'm connecting AT on the Q terminal, AT bar on the Q bar, clock to the C, AT plus 1 to the D. Preset, I'm making it always logic high. Reset, I am taking in from the primary input. Similarly, for the next flip-flop, I have these connection with the BT bar, clock, and X going into according to this circuit, with the preset staying at logic 1 and reset feed into from the input of this circuit. And then, questions so far on this implementation? Okay, now how the test bench look like. So we instantiate. Test bench is like structure-wise simple. It has one register and one clock generator and reset signal generator, or that registers, and an output for the observation as a where Z. So Z is connected to the machine's output, X is connected to the machine's input, machine's clock is connected to the CLK, and reset is N reset. And then I defined an integer and I defined a 32-bit pattern with a sequence of like this. So our expectation is this, that this part, after this is done, output goes to high, and at least it will toggles. And then at this point, it will become high. And maybe at the, no, 1101, this one will be high. So 3 blips maybe, I think so. Yeah. So, and then to start with, I have this X, the input bit pattern to 0 and reset signal to 0 and clock also set to 0, logic 0 to start with. Then at the 2 nanosecond, I am setting that reset signal to 1. That means within first 2 nanosecond, my machine is resetted and these terminals become 0, 0. And then I wait for a 4 nanosecond, and then in a while loop, I am basically extracting the bit pattern from the MSB side. So setting the X register value with the MSB of this pattern integer, which holding an integer, and shifting that pattern right shift by 1 bit. So essentially in the loop, each 10 nanosecond, I will be getting a new value for the X, that is incoming new bit is coming onto the machine. And at this point, after this loop is done, after 10 nanosecond, I have a stop. And then I have a always block, which always keep toggling clock to its like inverted form each 5 nanosecond. That means I have a 10 nanosecond clock period. So with this, if we now load that test bench, this one, okay, and let's load this 4 signal at 12. Okay. Maybe this one put on the data flow, crossing my finger if it doesn't crash. Okay, let's just fold everything. Fold everything. Okay, so you see the whole overall machine is that I have a 1 bit incoming pattern, 1 clock going in, 1 reset signal, and there is 1 output. And every state machine is within that block. I simulate it. Okay. So once I'm done simulating, I hope I have the correct values. Okay, let's see. So I have this clock signal always toggling, and let's say I have a 1 here, maybe 1, 0. Now it is going 1, 1, 0, 1. So see, it is bleeping here, and then it's bleeping here. So is it correct? 1, 1, 1. Okay, 1, 1, 0, 1. Yeah, so it is basically recognizing that. And then I have this is going 1, 1, 0, 1. Okay, this is good. Yeah, I think this machine is working okay. Like it is recognizing the incoming bit pattern and saying that if it sees the last 4 bit as 1101, and yeah. Question? Okay, so let's take 5 minute break and then we'll be back around 8:10. Okay, let's get back. 5-minute break is over. Uh, so Catherine requested me to go through one sequential design problem in the class. So let me try to do it. Uh, so let's pick up a problem from the problem set. On this lecture 6 to 8. This problem, design a 3-bit sequence comparator which has 3-bit data input, ABC, and 1 clock signal. I'm not mentioning about the reset signal there. Reset signal is there always. We assume that. No need to explicitly say. And it has 1 output. So, and this circuit is a 3-bit sequence comparator, which basically matches the values of this incoming bit stream. And if they all matches 3 consecutive time, output becomes 1. So in this example, see, it's coming in 0, 0, 1, so it is not matching. Then 0, 1, 0, not matching. Then 1, 1, 1, matching. 1, 1, 1, 2 matching. 1, 1, 1, 3 matching. So that is 1. And then 0, 0, 0, fourth matching, that's another 1. And then 1, 0, 1, not matching, that's 0. And 0, 0, 1, that's not matching, that's 0. So that's the problem. Question on the problem? Okay, now how do we solve it? Okay, okay, let me go back to the Jamboard to solve this problem. Okay, so we have this machine. A, B, C as an incoming, and then it has a clock. Now, what we need to think of, like how we can design it on the paper pencil. Okay, the limitation of the paper pencil method is that with the K-map, we can handle only like 4-bit truth table, right? That means we need to keep ours, like the entire input set, under 4 variable. Here in this problem, you see there is already 3 variables, ABC, as a primary input. Then to make it a 4th one, I have to make only limited on myself to the 4th one. I have to make the number of state as 2, like one is represented by 0, another is represented by 1. It may not possible. Like if I go beyond 2 state, it will be a problem for me in terms of K-map solution. It becomes like 5 or more variable scenario in that case. So what I want to do here to simplify the process, let's say what this whole meaning of this problem, like let's say I have a stream A, B, and C. Let's say like this, right? Then really my outcome or matching, let's say M as a matching partner is where it is matching. This point, so it should be at 1 now. And then this point, and this point as well, right? So 1, 1, nothing else. Oh, here is one more match, 1. Everything else is 0 as a matching result. So we can think if there is a circuit to match the incoming bit storage, a bit pattern A, B, C, and M, and this M is fed into my matching, 3 matching recognition, and that gives me the Y. So that way I have like 1 input, primary input, then I can play with 3 more Boolean variable. That is means number of state I can have in my state machine is like 2 to the power 3, 8. That means, which makes my life easier. And of course, this signal match is nothing but a combinational problem, right? It's basically we are trying to determine if at one point of time these 3 input is equal or not. And we can well construct a truth table for that problem, right?
Sorry,
So
Professor.
yes,
If you don't do the match box, how many states would you have?
it depends on what kind of state machine you are trying to build. And remember, the state machine, the design is basically very custom. Like there is no, this is more arts than science. So one specific problem statement can many state diagram. It's depend on a designer.
Okay, thank you.
So A, B, C, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Did I miss anything? Okay. 1, 1, 0, 1, 1, 1. Right? And for that, I know this is match all 0, all 1 is a match, right? Everything else is 0. And with that respect, I can definitely make it into a K-map. And this is a combinational design. Combinational design. So we can do this machine. Now from that, I want to make a state machine, right? With a match as an input, with a match as an input. So what I can do here is like make a state, that's initial state S1. And that's also initial state, which is symbolized by this. And then we can say we are operating on this variable M, right? If M is 0, not matched. M equals 1, that means matched. So that means if M is 0, I will go to the same state with output 0. But if it is 1, I go to the next state saying that I got 1 match, okay? And from that, if I get another match, M is 0, another match, M is 1, I will go into the second state, S3, 2 match, right? And if I go another match, now I stay onto the same state with output 1, which determines that, hey, I have 3 match, then I won, right? And then it might be that coming another match, like this will be like overlapping matching of the sequence. In that case, like just like this, right? Match. So 3 match, and then I know like, okay, 1 match, 2 match, 3 match. So I don't have that sequence. But what I'm saying is that maybe I could have like this one as maybe as 0, like this will be have a 1 there. So it is a consecutive match, like 1 1 1. Okay, I matched another one. I match on. So this is a 3 consecutive match. This is another 3 consecutive match. So that's the part I am handling here. Like I am hoping that there will be more matches. Now, if it is an unmatched from this state, of course, I go and reset myself. Like it's not matched, then I need to start again, like match. Even from the S2, if I get a not match, I start from that not matched state again, and state 1 is not matched. This should function as my matching 3-bit sequence comparator recognition. So far, so good. Any question?
Professor,
Yes.
concept of drawing the state diagram, like similar to the concept of drawing like a finite automaton or something?
Exactly, because the finite automaton is the base of the computer system. In fact, I think you guys studying the Turing machine and all, that is a conceptual computer machine which can theoretically solve any problem or any finite state problem.
Okay, so does it matter if our state diagram looks like a non-deterministic or a deterministic finite automaton?
It has to be deterministic, because non-deterministic automaton, you cannot just make a digital circuit out of it.
Okay, sounds good.
Okay, and I forget like exactly that finite state automaton has some concept of the input or output. It definitely has some input. What do you call it there?
It doesn't have output.
It doesn't have output, right? But in this case, we are basically have this output as well. So that's one difference, the state diagram. But it is finite state automaton diagram basically.
Okay,
Your computer, in a big sense, all the modern computers you're looking at, it's one big finite state machine. So now from here, next part is easy. This is the hardest part of an sequential circuit design, and then it comes to your state table, state transition, right? So we can look at this and make the state transition table as this one. So says state transitions table has what? Present state and next state. It has 2 possibilities, m equals 0, m equals 1, and output with m equals 0, m equals 1. So we basically then say that, hey, if it is S1 and if it is M0, look at the state diagram, it is M0, incoming match is 0. So next state is S1. And if it is 1, then next state is S2. Oh, next state is S2 with output at this point m is 0 and this 0, right? And then if my state is S2, then if it is 0, I go to S1 with output 0. And if it is 1, I go to S3 with output 0. Now from the S3, if it is 0, I go back to S1, output 0. And if it is 1, then I stay at S3 with output of 1. So that becomes your state table. Now from here, I want to make the state assignment. So one strategy for that would be, like, I have a 3 state, so I need minimum of like 2 bits for that. So I'm assigning them as, let's say 0, 0, S2 is 0, 1, S3 is 1, 1, let's say. Okay. So what I do here, then I replace S1 with 0, 0. So this is like next step, okay? So we are replacing the literal from the table to its numerical or binary sequence. So S1, 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 all the S1, okay. All the S1 goes to 0, 0, 0, 0, 0, 0, 0, 0. And then S2 will replace all the S2 with 0, 1. S2, then any other S2? No, okay. So 0, 1, 0, 1, and all the S3 with 1, 1. S3 with 1, 1. Okay. Now from there, the tricky part is to construct the truth table. Okay, the truth table. So let's say let's call this guy as R, variable R, let's say. Just arbitrarily, it is nothing to do with the latch RS or something, just arbitrary name, R and S. So Boolean variable R will be representing this part of the state diagram, higher bit, and Boolean variable S will represent this lower part, lower bit of the state encoding. From that, what we do here is we define the table, okay, with, let's say, primary input would be M and current state, RS. That's on my input side. Output side, I have R next. So that is the next state values. S next, and there is out. And let's give it a name on the output of the machine, which is, oh, which was already there, right? It is which was Y. Y was the output. So let's use that, Y. So we take the present state 0, 0, 0, 0 with M equals 0. My next state is 0, 0. So that means 0, 0. And Y is 0. Now we look at the current state 0, 0, and M is 1. Okay, so current state 0, 0, M is 1, which will give me the next state as 0, 1, 0, 1. So 0, 1 and y as 0. Okay, so I complete that. Now from current state 0, 1, so 0, 1, with the M0, I have next state as 0, 0, and output 0. And then with the current state 0, 1, with input M1, I have next state as 1, 1. Okay. Now, and output 0. Now with current state 1, 1, with M0, I will transition to 0, 0 with output 0. Right? So 0, 0, output 0. And with current state 1, M1, I will transition to state 1, 1 with output 1. So that means 1, 1 current state, input value 1, next state 1, 1, output 1. So that become my truth table for the sequential machine. And then we can actually make equation there, right? Y equals sigma m of, okay, what is this m? Let's determine this value. This is m0. This is m4. This one is, like, I'm just looking at this combination of this value, right? This is m1. This one is m5. M5. This one is m3. And this one is M7. So that means Y seems like M7. And by the way, we need to determine the don't care term. What are the don't care terms? I have 0, 1, I don't see 2. So don't care term is 2. Don't care term is 2. I see 3 is there, 4 is there, 5 is there. I don't see 6. 6 is a don't care, and 7. Okay. So that's all. 0 to 7 mean term. Don't care is to 6. So that's my equation number 1. Then our next equation would be sigma m of m5, don't care to 6, and S next will have sigma m of 4 and 5, and oh, 7, also 7. So far, so good.
Shouldn't 7 be included for R next as well?
R next. Oh yes, thank you very much. Yes, that's true, because R next is 1, 1, 1. Oh, R next is 1 with the M7. Thank you. So yeah, 5, 7, 5, 7. Okay. Catherine, this making sense?
Yeah.
Okay, now from there, you can actually have the K-map and etc. Use use D flip-flop for this, implementing this R, like D flip-flop, and what it will be like this, like this Q is really your R next, where the D is really your R. Okay, in the Boolean table. Okay, this is belongs to Q is belongs to R next. Oh, sorry, my bad. Take it out. It's a different. It's the other way. Okay, this is really your R, and this guy is your R next. With the clock and etc. there, clock. It doesn't have the symbol. reset, etc. is there, but mainly is that with this state variable, for each state variable, you will have one D flip-flop whose next state is coming, next state logic is coming into the D, and Q is the present state logic. So that way you define the construct of the circuit. Question. Yeah, so you can go to this the solution of this problem, and you can see the what elaborated that circuit diagram, K-map, etc., etc. Do it yourself. The main challenge is basically to come up with the state diagram. From there, make it a state table. From that point, make a state assignment with number of bits, and replace the state table literal name with the state assignment values, and then from there to the truth table. So that these are the challenging part. Once you have the truth table, you determine the equations, logic equations, and there you go. You can use the K-map and everything to make the circuit work. Question?
If there's not anything more important to get to, I think I just have a question going back to the very beginning. I may have missed a key bit, but when you make a logic equation for it and you say that m is equal to, I'm looking in the like actual like answer in your like the PDF of the answer, and where you say that like m is equal to A or B, or like A apostrophe B apostrophe C apostrophe or ABC. Why wouldn't you just want it to be ABC if you're testing if it matches? Why would you want it to be all the same or all the opposite? If that makes any sense. Sorry, I think I might have missed something important there.
Okay, so this is the one, right?
Yeah.
To table the first part is following: A bar, B bar, C, or ABC. So what's your question again on this part?
Why would we want it to match if none of them were the same? Or
no, this is all the same, right? All zeros, they match.
Oh, sorry, yeah. Those are the actual input bits, not the do they match in that area. Got it. Okay, thanks.
Yeah. Those are the actual bits. Everything else is a mismatch. That's right. Yeah. Okay, then. Okay, let's then stop tonight if we don't have any other question, and then see you all on the Wednesday. And we'll continue with this lecture 8. By the way, these 2 days is on the lecture 8. Lecture 8 is really big. It has a lot of discussions. So I have broken it down into 2 parts. Like one is we go with this sequential circuit design and the common components like the multiplexer, decoder, etc. And then we'll move to the registers, which are a little bit tricky storage element, but which is you need to understand really on that part. So 1 lecture, 2 days, you time yourself on those parts.
Does that mean we're not expected to watch lecture 9 videos before Wednesday?
No. This week all about lecture 8.
Okay.
Oh, of course, you can start up front on lecture 9. I'm not preventing you. But yeah, this week we'll spend time on the lecture 8, I believe. Yeah. Just I want to make sure that while I make that comment, I have somewhere my schedule. Where is that? I'm just looking at the schedule. Okay, so today is 21, right? 21, 23, yeah. 21, 23, both of the days we will be on the lecture 8. Then on next week, we'll move on to the next module, which is addition, subtraction, etc. Those circuits. All right, then. Good night, everybody, and see you on this coming Wednesday.